And then Donlea, I think, are you teaching at a specific grade right now, Donlea?
Oh, Amanda, are you calling me?
Yeah. Oh yeah, actually, Amelia, yeah, you said you're at high school, right?
Yeah, I'm juniors and senior students.
Wonderful. Okay. And Donlea? What grade are you working with a specific grade at this point? It's good to see you.
It's good to see you too. I'm working with 6 through 12 in ISTEAM, Indigenous Science, Technology, Engineering, Arts, and Mathematics.
Awesome. Great to see you.
6 through 12.
Okay. Okay, so since we have such a wide range here, I'm going to try to make sure that we spend a little time at many different grade levels. But there will be some that's more for younger kids and some that's more for older kids. So hopefully everybody will find something that they can take away from today. We're going to be talking about number sense and some different ways to help students develop their number sense, and also some algebraic thinking skills that go along with that, looking at patterns and things like that. So we will jump right in. I'm going to share my screen. And again, I put in the chat all of the link to all these documents, and I think I'll also send them to Dave so he can send them out later. The first thing that I'd like to talk about is a little bit of 3 stages for scaffolding computational skills to develop number sense. So whenever we're teaching addition, subtraction, multiplication, or division with any kind of numbers, whether this is just with single digit numbers for kindergarten students, or whether it's working with, for the first time with integers or signed numbers in middle school, these stages are things that the students should pass through. So we don't want to start by just teaching them to memorize or teaching them the rules. Instead, we want to have them pass through some stages where they first, in the stage 1, they learn what it means. So that in this stage, they should be learning how to picture that. So what would it mean to do 4½ divided by 3/4? How can I think of a situation where I would do 4½ divided by 3/4? What would it, and how could I draw a picture to find the answer to that problem, you know, or model it with objects? You know, same thing for younger kids and for older kids as well. What does it mean to add, you know, to subtract, say if I want to do 2 minus -3, how can I really represent that concretely using a model and understand what it really means? So that's stage 1. And then stage 2 is when we move into being clever, noticing patterns, discussing with each other their ideas and their insights, and using strategies. And some examples of that are, if we're trying to do something like 7 plus 6 in 1st grade, we might realize that we can break the 6 into a 3 and a 3, and 7 and 3 gets us to 10, and 3 more gets us to 13. Or we could think of 7 and 6 as doubles plus 1, right? It's 6 plus 6 plus another 1. So if we already know our doubles really well, we can sort of get up to 7 plus 6 using that. Or if I'm trying to do 98 plus 98, I might think of that as 100 minus 2 and plus 100 minus 2. And so that's the same as 200 minus 4. There's a kind of a sneaky trick here, trying to understand numbers as the distance between the 2 numbers. So if I'm doing 130 minus 58, I'm thinking about how far apart are those numbers. One thing that we can do to be, that makes this problem easier is to shift both ends. So instead of thinking of it as 130 minus 58, it's the same thing as 132 minus 60. That distance and the other distance are the same because we just shifted that bar up 2 units and on both ends. And so we can work that problem out more easily. 7 times 6, here's another strategy that students might do. They might know, be able to figure out 7 times 5 pretty easily. So 5 7s is 35, and 1 more 7 would give us 6 7s. Or I could think of 6 7s as being 3 7s and 3 more 7s, which is 21 and 21. I could do something like 5 1/4 minus 2 7/8. I could get a ruler out start at the 2 7/8 mark and kind of hop up until I get to the 5 1/4 and work it out that way. So this is just using different strategies and basic number sense to work problems out without having the formal rules or the memorized steps that come later. And then finally, the third stage is to just get that fluency down. So that's where you are talking about memorizing your math facts and knowing your sort of standard algorithms pretty fluently, because comes a time when you no longer want to spend all class period trying to figure out how to multiply two numbers, and you just need to be able to get that answer so you can do something else with it. However, one thing that's very important to remember here is there sometimes is a tendency to rush students to the third stage without giving them enough time at stage 2 or at stage 1. Especially this is true, I would say, in middle school. It's very common for when teaching fractions, especially in books, a lot of times the books sort of rush them from a pictorial representation straight to the algorithm, or they don't even do the pictorial representation for, say, division. They just right away teach them, and you're just straight at stage 3. I think it really is important to make sure that take a look at your curriculum and make sure that you're filling in concrete representations first. Even at those older grades, they still need to understand what it means. And then make sure that there's plenty of time for them to develop their own strategies and ways to be clever, ways to do it more than one way, and talk about those ways. Before getting into stage 3, where we're just rushing to get the answer and follow the rules. There is a temptation to rush to stage 3 because it is in some sense the easiest. Chanting back 6 times 7 is 42 is easier than understanding what 6 times 7 means. So that's why it's tempting, always tempting, to go for the easy thing and rush to that stage 3. But we want to make sure that we spend plenty of time, like I said, at stage 1 and stage 2, which is where the real thinking happens, and that's where the number sense gets developed. Does anyone have any comments or questions about that? Has anyone had an example where they've done some work with stage 1 or stage 2 that they'd like to share? I'm going to stop sharing my screen for a second. Especially some of our people who are working with K-8 students. Has anyone done any stage 1 or stage 2 where you've used models or you've used strategies to talked about strategies with your students? All righty, well, we'll come back. If anyone has an example later, you're welcome to share out. Okay, so let's go back in. On the back of this document, I do have a chart that shows what grade levels the 3 stages should be occurring at according to the Common Core standards. And in this chart, the way it works is, so this is, say, adding and subtracting within 5. And basically, kindergartners go all the way from stage 1 to stage 3. And first and second graders are mostly at stage 3 with that skill, because they should have the basic operations within 5 pretty quickly on their minds. But these are sort of the grade levels. For example, if I jump down here to fraction, representation, and equivalence, that begins a little bit in 2nd grade and a little bit more in 3rd grade. But really, we need to keep that representation of fractions going all along. That's why this says 1 to 3. Even up in 7th and 8th grade, I often find that my students need physical models of fractions and how to represent them, because they may not really understand what a percent means or what the decimals are about. And so going back to that is very helpful, and that's why those 1 through 3s are in there. So that's what that document is.
You talked about visual there, Amanda.
Yeah, David, go ahead.
Whenever things are divided by 2, I just end up using a regular sheet of paper, fold it in half, fold it in a quarter, fold it in eighths and stuff like that. And, that's pretty visual.
Absolutely.
When you get to odd denominators, a little bit tougher, obviously.
Yeah, absolutely. Although one really good visual for fractions of almost any size, at least, is to use just grids. So if you're trying to do, 21sts or 24ths or something like that, a circle model is a real pain to do, even 24ths, because you try slicing a pie in 24 pieces and you kind of get crumbs. But if you make a 6x4 grid or an 8x3 grid, it's really easy to see all the pieces very clearly in that kind of model. So grids, I do want to put a plug in for grids on fractions as a good model to be versatile for any number. Okay, so one really good way to do the second stage, because we've talked about the stage 2, and this developing insights and strategies is where the real thinking comes in. And it's where the most important thing about this stage is the students do the talking and the explaining to each other. And so one really good way to do this is called a number talk. And basically a number talk is where you gather the students for 5 to 15 minutes together. Often you pull them away from their desks and sit together on the floor. Well, you don't have to do it that way. And basically it's a conversation about some different strategies for solving a given problem. And this some sort of summarizes what the goal is and how it might look. Basically the teacher is presenting a problem to think about, and then the students figure out the answer and then share their answers and share their thinking. And we try to make sure that we're talking about more than one way we could figure it out. And then the final, then the class talks together about what they think is really the answer, if there's some disagreement about what the answer might be. And then you might do other problems like that if you wanted to make it a little longer, or you could just do one problem to make it a short and sweet intro on the class. And this is a good idea to do even for older students if you feel like maybe they need a little bit of work on fractions, or they need a little bit of work on even multiplication and division problems, or sort of mental math strategies for higher higher problems. So this is something that can be done. It's very important to make a safe environment and make sure that the students are feeling supportive of each other and listening to each other. This is something that one of the teachers that I've worked with uses. She found this sheet, and she basically said, what do mathematicians say when they don't understand? So she's encouraging her students to say these things to each other. Could you explain that another way? I don't understand. I have a question about, can you tell me why you think that? I'm still fuzzy about this. Can you tell me more about your ideas? What do mathematicians say when they agree? So her students should say, I agree with her results because, or my strategy is like yours because, or I agree, can I share my strategy? What do mathematicians say when they disagree? I disagree with your answer because, or I got a different answer because, can you prove your answer another way? And then how do mathematicians complement others? And so the students saying to each other, that was efficient, I like the way you did that, or wow, I'm going to try that next time. So getting the students to comment on each other's ideas is a very important thing. And these are sort of like conversation starters that she uses to get her kids talking with each other rather than just to her. Okay. This is another activity that can be done this way. This is number of the day. And number of the day, you just give a number. So for example, maybe 525. And it could be that you're asking your students to give you different ways we could make 525, and then just brainstorm as many ways as you could. What I'm showing on here on this page is that sometimes you can get students to riff off each other. Maybe the first person put 500 plus 25, and the next person said, oh, well, I could make that as 100 times 5 plus 100 divided by 4. This is obviously an example for some older students, but you could do number of the day with really young students where they're just riffing off each other using addition and subtraction, or using different kinds of tally marks or that kind of thing. I'll show that down lower. Here's 100 times 5 is here, but then I could break up the 5 and make it 100, 8 minus 3. I could break up the 100 and make it 20 plus 80. And so see how as we go down, these expressions get crazier and crazier and crazier, but each one is just taking the previous line and making it a little more exciting. And so you end up with this crazy expression at the end that they develop by just making it subsequently a little crazier and crazier. This is a fun way to introduce all kinds of different techniques and operations to your students and getting them thinking creatively about numbers. There are some other ways to do this. Once they're good at number of the day, to ask them to do a secret equation game where they choose their own number of the day, generate some expressions, and then set two of their expressions equal to create a secret equation. And then they can replace one of their numbers with a symbol or a letter, exchange with the other group, and try to get them to figure out what the missing number was, what the what the letter is replacing. And you can do this with anything from kindergarten through 8th graders, as long as you, for kindergartens, probably keep it a little simpler, not too long, but they can all do this. Here's an example for 1st graders. So number of the day would be 78 maybe. They could draw tally marks, coins, or paper money, base 10 blocks, show it on a reckon rec, or an abacus. They could use addition, subtraction, multi-operation expressions with an answer of 78. And this can be implemented as a circle activity by giving student a different manipulative and asking each one of them to represent the number of the day. So maybe one person has is going to use tally marks, another person will be using money, and one person will be using base 10 blocks. So they all sit in a circle and they do it all a different way, use a different set of manipulatives. Here's an example for what it could look like in 4th grade, using expanded form. And then here's an example for some examples for the secret equation game. And then here's sort of a blank page if you don't know, sort of at the 4th grade level to get them to do the number of the day and to do the different forms. So I have those in there, and there's also the standards that are related back in that. Let's go ahead and play some of these games here. But before I get into this, I want to stop one more time and make sure, does anyone have any questions about number talks or comments? Questions or comments about the number talks, about having conversations with kids, about strategies? Do they want me to go into strategies for a specific kind of operation? Anything like that that we should talk about before we get into our game? Okay. Alrighty then, let's go ahead and get into our game. And the first game that we're going to play is called bowling. And so I'm going to give you 4 numbers, and then the goal of the game is to make the numbers as a team. You're going to try to make the numbers 1 through 10 using those numbers. So this is sort of a target practice game. So for example, if I'm trying to use 5, 4, 4, and 3, the rule is I have to use just those 4 numbers and all of those 4 numbers to make the number. So it wouldn't be okay to just do 5 minus 4. I need to use the 5, the 4, another 4, and a 3. So here is one way to do that. I could take 5 minus 4, which is 1, and then I could multiply that by 4 minus 3, which is 1, and 1 times 1 is 1. So that works. Here's a way to do 2. I could do 5 minus 4 plus 4 minus 3. That makes 2. So this is the goal with the bowling game. You can use addition, subtraction, multiplication, division, any of those operations, and you can use parentheses. And your goal of your team is to try to figure out a way to make all the numbers 1 through 10. Oh, here's a clever one for 9, using concatenation, like make it a 53 minus 44. So you're allowed to stick digits together if you want to make a larger number that way too. As long as you use the 5, the 3, the 4, and the 4, it's all good. So I'm going to go ahead and give you guys the numbers. So I'm going to put them in the chat to make sure everybody's getting them. But then we're going to do breakout rooms. So make sure that everyone should jot these numbers down that I'm going to put in the chat. I'm going to put in 2, 6. I'm going to sorry, 7 and 9. So there it is. It's in the chat. 2, 6, 7, and 9. Your goal when you get into your breakout groups is going to use 2, 6, 7, and 9 to make all the numbers 1 to 10 as a team. So let's see how we do with that. Dave, are you able to make, I guess I can make up breakout rooms. Here we go.
Maybe 4 rooms would be good.
Yeah, let me see if I can recreate them. Okay, there we go. So I've got everybody in rooms. I'm going to open them. And like I said, make sure that you've written down the numbers 2, 6, 7, and 9 so that your group can work with them in the breakout room. Everyone got any questions before we go? Okay. Let me see if I can open this. Oh, I'm doing the wrong thing.
You want
Sorry
me to
about
do
this.
open all rooms?
Yeah, I'm trying to get back there and it's not letting me. Can you open them?
I think I just did.
Okay,
I've got
awesome.
a bunch of unassigned people that I'm just going to start assigning.
Yeah, and put them in room 1 because there's only one person in room 1. I'm not sure why that happened. Okay, here we go.
So we might be in rooms, but have you sent something for them to do?
Yeah, they should all know what to do. They should all be making the bowling with 2, 6, 7, and 9. But I'm going to go visit and make sure everybody knows how to use a whiteboard. And I'll go to all the rooms.
All right, I'll also join rooms. Hi.
Hey, David.
So did you understand, Amanda was hoping somebody would open up a whiteboard and try the bowling with it. So does somebody want to try an attempt at the whiteboard?
Oh, let's see here. Oops. What was this? It will. I would like to, but unfortunately, my computer is not cooperating with me. So, is somebody else available?
Well,
Let's see. Come on.
in the worst case, I can do it, but
Okay. Let's see. Nope, none of my, it's not coming up. Let's see.
yeah.
Is anybody else able to open up and do
I
a
can
whiteboard?
do a screen share. With me. All right, so I think I've got something up that I can take notes for us. Do- Does somebody want to pick 4 starting numbers?
So I think the starting numbers are that we have are the ones that she gave us were 2, 6, 7, and 9 that we're going to have to use to get our numbers 1 through 10.
Excuse me. Okay, so maybe I'll check pen color and see what. So in fact, I can make a list. Is there any reason you need to do the numbers in order?
I don't think it necessarily has to be done in order. I think just as long as we've accomplished a task of doing 1 through 10.
Oh, great.
So I'm just a note taker.
Okay, so for number 1, I have 2 times 7, which will give us 14.
In
and
parentheses or?
Yeah. I didn't do parentheses, but I'm being a little lazy today. So,
Okay.
which will give us 14, and then minus 9, which will then they'll give us an answer of 5, and then minus. Oh, that'll give us -1. Okay, this is why I'm in a math
If you can
class.
get -1, then maybe you might be able to edit it to get your one.
Yeah, maybe we could do a +6 or -5. We could edit it that way. Yeah, start introducing our integers here, because I really don't think she said that there was like any other guidelines other than use math to find the answer. So, all right, I'm going to play around with this one to see what I can do to get a +1 instead of a -1.
So are we going to think of an equation that will be equal to 1?
Yeah, that's what we're trying to do. And so we had our first guess was pretty good. It was, let me come here and type it in. The trouble was it got us -1. And so instead of subtracting so much and adding so much, you want to have it so that so can you change things around? Another thing we can do is I can make some scratch work. One of the reasons I like putting the scratch here is it allows you to just say stuff, whether it's right or wrong. It's just stuff. And part of doing math is just trying things.
Okay, so I think that if we were to, wait, nope, that's not going to work. Still working on it.
What was your idea? Say it, verbalize, because maybe you'll inspire somebody else to, it doesn't have to be right? Let's just stick it in.
Okay, so what I did was I switched the two, or I made it a 2 times -7, which then would give us a -14.
Uh-huh.
And then -14 take away 9, and then you keep change, that would give us a -5.
Wait, -14 minus 9, you're $14 in debt. You're gonna then spend another 9 on the charge card.
Yeah, and then it would give us a then we would have, yeah, and see, that's where I'm like, that's where I messed up, and I'm like, okay, that didn't work.
Okay.
So yeah, still playing around with this.
Okay. Other folks in the room have other things to try, and you can just put together arithmetic with these things, and maybe you get other numbers that you can combine together.
Yeah, we could add also.
So like what kind of things, where do you want to add? Is it in Scratch or in Blue? Or? I just add any numbers, see what you get. Subtract any numbers, multiply.
All right, so I kind of abandoned the number 1.
Okay.
And I found an answer for 10.
Oh, what'd you get for 10?
So for 10, I just did simply 2 plus 6 plus 9, take away 7.
Sure.
So yeah, that's my contribution.
That's a great contribution.
But I will have to go back, because now number 1 is driving me crazy, and I have to figure it out. So I have homework.
Well, can you change a negative into a positive? If your answer was -1 and you wanted +1, is it good enough to just change one side?
Yeah, that would be, and then we could get the right answer for it. But yep. Anybody else, Lance, Patricia, that have some? Evelyn?
Oh, I have 9.
Oh, how do you get 9?
7 times 2 minus 5.
7 times 2. Then you said minus
5.
minus 5. How are we getting 5?
It's 14 minus 5. So 9.
But the role here, part of the goal of this is, oops, nope, I did not want to do that. The goal here is to try to use these numbers, the 2, 6, 7, and 9.
I saw it. There's no 5. Maybe that's for. I think that's possible also for 10. But anyway, I'll just think another.
Sure.
It could be for 7 times 2 minus 6 is 8.
Minus, but we have to use all of the numbers. So that's good. I mean, once we get 8, we could do that. So we're getting 7 times 2, that's 14. And then you subtracted 6 minus 6. So that's equals 8. And we haven't used 9.
Oh, yeah.
So can we get something else? Because we could combine.
So we need to use that 4 number just once, or we could.
Yeah, you have to use each of the 4 numbers once. But part of this is a great trick when you're solving like those peg puzzles you see in a Cracker Barrel restaurant. If you can solve a part of a puzzle and solve a lot of parts, like I'm writing down in the green, you can often put those together to solve a bigger puzzle. So here you've built 8 and you have 9. What do you do with 8 and 9 to get, say, 1?
8 minus 9 will be negative 1.
Which is one thing that we've discovered, but that was close because it. But if you wanted plus 1, yeah, we're getting this pesky negative 1.
Can we add 2 more?
What do we do to get plus 1?
Negative 1 plus 2.
You see why I'm saying just with 8 and 9? Because we've got 8 using these 3. So we're using these 3. So it means that you just need to plug in 9 somehow.
Mm-hmm. Yeah, it's not easy.
Can you make a story or a description that would say, hey, I want to have 1 left? You got silence here.
I got another, shucks, I see we're breaking up, but I've got another one that would answer for
if you've got $8 and you want to buy something that costs $9,
yeah,
you're $1 short. Could you say it just by using the word dollar to get 1?
Yeah, we could do that. We could fix that one for the first one, and then that way it does work as a possible answer for getting 1. But this definitely takes a whole lot more using our brain power than a Saturday morning allows.
I think we're all going to go back.
Yeah. All right.
You were close. You got started.
Yes. And I'm yeah, definitely.
Group 1. Let's see what answers we have for number 1. Can somebody from one of the groups just tell me what you guys got for 1? Was anyone able to find number 1 in any of the groups?
We did, but I'm looking for my PowerPoint.
All right. While Reva's looking for that, did anyone get number 2? Does anyone have an answer for 2?
I have one. I put it in a chat box.
Oh, great. Let me see
Is
if I
that
can
for
see.
1 or 2? Who just put it in? Was that for 1?
That's for number 2.
I wonder if I can actually see the chat. Oh, there it is. I can see it. Aha. So, thanks, Delana. I see it. So 7 minus 2 minus 9 minus 6. So that's going to be 5 minus 3. That's 2. Yay. Excellent. Does anyone have a different answer for 2 that we should put while we're here? All right. There's 1. Does anyone have one for, let's see here. Reva, did you find the one for number 1 yet? I know you're pulling up your PowerPoint.
Not PowerPoint, my little, what is it called? Whiteboard.
Your whiteboard.
I can't get a hold of it in our chat. I didn't take a
Gotcha.
picture of it.
Oh, so sorry about that. Okay.
Amanda, I can give one for number 1.
Yeah, go ahead.
Okay, so quantity 6 divided by 2.
Yep.
And then subtract 9, quantity 9 minus 7.
Nice. So that's a way to make 3, and then 9 minus 7 is 2, so 3 minus 2. Very good. Does anyone have one for number 3? Way to do this. Oh, that's a nice one. Delana put in the chat 72 minus 69. Very nice. Okay. Any for 4? Was anyone able to find number 4?
Okay, number 4. 6 plus 2 inside the parentheses, and then divided by 9 minus 7.
Good. So 6 plus 2 is 8. 9 minus 7 is 2. And there we got it. All right. How about number 5? Did anyone get number 5? Aha, I've got one for 6 in here. So 9 minus 7 times 6 divided by 2. Thank you, Eliseo. So that would be 2 times 3. So that's perfect. Any other ones for either 5? Anyone get 5?
Someone in Reva's group did get it.
And we lost it, didn't we? Yeah.
I know, but I have it written down also.
Oh,
9 times 2?
Yes.
Minus 7 minus 6.
Oh, nice. Very good. Okay. Did anyone get 7 in any of the groups?
It's 9 minus 2.
9 minus 2.
Parentheses.
After the 2?
Open and close.
Oh, around the 9 and the 9 minus 2? Go ahead.
And then times.
Yeah.
Parentheses 7 minus 6.
Nice. So 7 times 1, basically. Okay, great. And Griselle said she had another answer for number 6, which is, let's see here, 2 plus 6 plus 7 minus 9. Nice. Okay, any others for 8? Anyone get 8?
So 8 is quantity 9 minus 6. And then plus 7, quantity 7 minus 2.
So 3 plus 5. Awesome. And how about number 9? Anyone get 9?
Number 9 is the square root of 9.
Good.
Times 3 equal 9.
Yep.
But you're supposed to use all the numbers, right?
Yes.
So 6 and 7 is missing.
Oh, yeah.
Oh, but you can do that. You can do that. Divided by 7 minus 6 quantity. That's right, Amanda. The 9, oh, she's using 3, huh? And there's no 3. Wait.
Yeah. I mean, we could do the 6 divided by 2, but then we have to lose a 7 somehow, right?
Yeah.
And that's the tricky part.
Yeah, it's because they're odd numbers. We can't really do the odd numbers because we have 9. So 9 is kind of like an odd number, a prime number.
Yeah. Well, I liked that. I really like that square root idea. Oh, here's one for 10. I'll take this one off for now while we think about it. And then there's a couple ideas for 10 in the chat here. So Rachel had it. 2 plus 6 minus 7 plus 9. And another way, which is 26 minus 7 minus 9. Both really nice ways. Does anyone else have a way to do 9?
9.
I actually think I have a way to do that. Let's bring back that square root of 9. If we did 2 plus 7 minus 6, then that would give us 3. And so then you'd have your 3 times 3. So I think we found a way to make that square root of 9 work, because I like that idea.
Yeah.
Nice, nice. Okay, there we go. So very good. So we're going to go ahead then, and let me stop sharing here. So this is just like I said, this is a fun activity that just sort of gets students thinking flexibly about numbers and how they can make other numbers. There are some other games in this packet that I have for you guys that are also good for this. The thing I like about the bowling is that there are many ways to be right. You know, there are lots of ways. You can, even if you can't get one of the numbers, you can get some of the other ones. So there are a lot of opportunities to come up with it. This is a game called Crypto, where you roll 6 dice, and then they just try to make equations that are true using as many of the numbers as they can. They don't have to use them all. And so that's a little less restrictive. There's one that's closest to 50. So you roll 4 numbers, and then they try to come up with a way to get as close to 50 as possible. And again, if they don't get right on 50, that's not a problem. This is called the 4-4s challenge, where you try to use 4 4s to make all the numbers from 1 to 50. And there's a couple symbols that are in here that are a little unusual. 4 factorial, 4 exclamation point. This explains it here, but it's equal to 4 times 3 times 2 times 1. So that's a way to get 24 with just 1 4, and that's useful for this game. Also, using a 0.4 is necessary for at least one of the numbers. I think there's another way to do 26, but this is an example of using 0.4. It turns out 4 divided by 0.4 is 10, because there are 10 0.4s in 4. And so 10 plus 16. But that 0.4 turns out to be useful in some other examples too. So I also put in the 7s challenge. So try to use as many 7s as you like, and try to make as many numbers from 1 to 50 as possible. So that's another example of some target games. I have another one here. This is also in the drive. These are cards from a game called 24. And basically you have the 4 numbers on the card and you can use any operations and you're trying to make 24 all the time. The cards with 1 dot are sort of at the easier level and 2 dots is a little harder. And then the 3 dots down in the file are even harder, more challenging. So there's some of those. I put in some pollinator puzzles here also. So let me show you how the pollinator puzzles work. These are from Gordon Hamilton, and these are really fun. Here, we're trying to use, we're trying to use all of the numbers from, from 0 to 9 only once. And in these first puzzles, the petals show that the boxes have to add up to that number. So right here, I see the number 17, and I know that there's only 2 ways to add numbers from 0 to 9 to make 17. Either it has to be 8 and 9 or 9 and 8. So I'm just gonna try it. I don't know which way is right. Maybe I'm wrong, maybe I'm right. Well, let's just try it. And then I'm gonna try to figure out, well, 9 plus what makes 13? So there's 4. 8 plus something has to make 15 out here. So this is going to be 7, 2, this is 1, 6, and then 6 plus 3 is the 9 up here. Looks like I'm going to have to put a 0 here. 3 plus 0 is 3, and then this is going to have to be a 5 to make 5. And so we have, this one worked. I got all the numbers 0 through 9 and all of the things add up the way they should. These puzzles can also, so there's, I forgot to clear my screen. Some of these are just addition. This one is, here is addition and subtraction. So inside the petals, it's addition, but the outside petals are showing the difference. And then over here, there's one with multiplication and
then lots of times I can only hear the voice.
Oh, is it, Rena, is it not coming through?
Oh, I'm sorry.
You're fine.
No, it's fine. I just was talking earlier about how my internet connection was unstable.
Gotcha.
Coming in.
Well, I'm glad you're able to hear me now. That's good. So we have multiplication on the outside here, and the inside is subtraction. And then there's some blank flowers where the students can make up their own puzzles for each other to solve, and they can use whatever operations they like. So those are some fun puzzles, and then these are some other puzzles that I'm going to skip on by. And all of these are sort of getting them thinking flexibly about numbers and operations. I think we're running a little bit longer, and I wanted to make sure that we get to something for the high school teachers. So I'm actually going to jump to the last one and skip over the NIM games. NIM games are really great as well for teaching. This one is showing how to do fraction NIM, and this is a really fun game for counting. And you can do this in other languages as well. So if you're trying to teach Navajo or another language, you can actually count in Navajo and have them play the game that way. Adding the numbers up to 20 or something like that. It's a really good game for developing critical thinking and number sense. But I'm going to jump down to the digits page, which is more for middle school and high school. And this one is understanding how patterns work when we're working with fractions. So and turning them into decimals. So let me give an example here and annotate. So if I wanted to do 1/7 as a decimal, then what I need to do is work out 1 divided by 7. Basically, I have $1 and I'm trying to share it with 7 people. I can't share a dollar bill with 7 people, but if I make it into 10 dimes, which is what this is doing, open it up into tenths, then I can give everybody 1 of those dimes, and that will give out a total of 7 dimes, and I'll have 3 dimes left. If I open up another 0 here and drop this down, I've got 30. So now I have 30 pennies, And I give them around to my 7 friends, and I can give them all 4. 4 times 7 is 28. And so now I have 2 pennies left. This bank that I'm working with doesn't stop at pennies. It has something which is 1/10 of a penny. And I usually have my students make up a name for all these little coins. And they'll call them things like teensies or tinies or other things like that. But anyway, we go down to the next one. And if we're going to call these tinies, then I have 20 tinies now. And I can give them around to my friends. So get 2 of those. 14. I'm just going to keep going, drop down the next. If I exchange 6 of the tinies for 60 teensies or something like that, then how many can I give to each of my friends? Well, it's going to be 8. If we keep going like this, we'll have 5 times 7 is 55. Subtract down to 5, and we get to 50. 7 times 7 is 49, and here is where we get back to the beginning, because we started with a 1 that turned into 10 dimes, and now we're back to 10 of a tiny little coin. And so at this point, it's going to have to start repeating, because when I share that around, I'm going to have to give everybody 1 again. And so we can see that the answer to this is 0.142857 with a bar. And what's really fun about this is that if we do this, the same process with 2 divided by 7, we actually get this, 0.285714. And if we do it with 3 sevenths, we get 0.428571. So what we can notice here is that the same pattern of digits is happening. Because if this were to keep going on, it would be 1428571, 1428557 forever. And notice that the 285714 is right here, and that's what this one is. So all of them really do follow the same pattern. They just start at different places. And so this sort of invites them to figure it out from the pattern, what they're going to get for these here. This one's going to have to start with the 5. The next digit up is the 7. And then, whoops, I got my 5. And then we have our 85714. So we can get all of these. Let me. I'm going to make a note for a second because we'll need it on the next page. Notice that the remainder of 1 at the first that we started with here, we started with a 1. It led to a remainder of 3, then 2, then 6, then 4, then 5, and then back to 1. So I'm going to write those down just so that I have them for the next page. So 1, 3, 2, 6, 4, 5, 1. It's worth noticing a couple things here. All of the digits from, that are less than 7 show up as a remainder in this example. So it isn't, this is one of the reasons that this number has to repeat no more than 6 digits, because if we ever got a remainder of 0, we would stop. Whereas as long as we get a remainder of 1, 2, 3, 4, 5, or 6, we would keep going with the process. But as soon as that remainder comes back again, we're done, and it starts repeating. So this is the reason that sevenths have to repeat with no more than 6 digits. And in fact, it does take 6 digits before the repeating part is finished. And so this is sort of showing the students that idea. If we actually draw a remainder web based on this, that's what this page is for. I'm going to try to get my annotation tool back. I had that 1 went to 3 in our remainder process, and then 3 went to 2, and then 2 went to 6. 6 went to 4. 4 went to 5. And then 5 went back to 1. So it makes this pattern. If you ever did get a remainder of 0, it would be 0 forever because you would have no more to share and you wouldn't have anything left. So this is what the remainder web for 7s looks like. And it doesn't matter where you start on this process, you'll always have the same pattern of remainders that repeats over and over again. And so that's why that pattern, you know, the digits 1 7th, 2 7ths, 3 7ths, all of those are going to have the same result. So let's try to figure out what 1/47 would be as a decimal. Now this time I don't want to just do long division. We can tell because it's the denominator is 47, we could have a remainder 1, 2, 3, 4, all the way up to 46. And that means we could have 46 different numbers in the repeating part. So let's try to figure out what that is, but let's do it using calculators. So does anyone happen to have a phone with them or a calculator to hand and can do 1 divided by 47?
Okay. So
Well,
1
tell me what you
divided by 1 divided by 47 is 0.0212765957.
All right, so yours goes pretty far. The 7 though, I don't know whether to trust that because it might be rounded from your calculator. So
Okay,
we're gonna throw that one away. But
Okay.
those digits are all trustworthy. So what we're going to do is I'm going to come down here and I'm going to, well, we'll keep going with this. I'm going to take off the 7. What I'd like to do now is I'd like us to figure out some amount of 47ths, which starts 0.595. So does anyone have a guess? Something divided by 47 that should start 0.595. One thing that helps is to realize this is more than halfway. So it's got to be more than halfway to 47. So can anyone find it?
Amanda?
Yeah.
Are you looking for the number divided by 47 to get 0.595?
Yes, exactly. That will start 0.595. Do you know what it is?
Oh. It's a 2-digit number.
Yep, for sure. It's got to be more than
27.
halfway to 47. So
27.
27, is it? Okay.
Yeah.
So tell me what you get for 27 then. 27 divided by 47.
28, isn't it?
Oh, is it 28 or 27?
Oh, so you round it off. Okay. Let me see.
28, it's going to be 5.595. 7 4.
So let me change that. Sorry, let me catch up with you. So 28 divided by 47, 0.595, then what?
595 744 6809.
6809. So what we can do with that is we know that this is sort of tying in to our pattern up here. So 595 744 6809. So I'm going to keep on tacking on to that one. Now again, I don't know if I can trust the 9 because it's the last digit, so I'm going to stop at 0. So that means that now we're looking for something that starts 0.680. So see if you can find on your calculator. It's going to have to be more than 28.
32.
Is that it? Okay, and what do you get? 0.680 what?
Hold on.
851
851
0638.
063
08510638.
8. Okay, and then we're going to throw away the 8 because we don't know if that's rounded. So we've got 808510663.
3.
All right, so now we've got to find something that starts with 0.063 something. So what should we divide by 47 to get?
Try 3.
3? Is that it?
Yeah, let me see. Yeah, that's what I have.
And what do you get?
Okay, 3 divided by 47. It's 0.6382978. Oh, there's 7 after that. 7 and 2.
So there's a 2 after that, you said?
2. Yeah, there's 2.
Okay, and the 2 is the one we're throwing away?
Yeah.
So 0.063 829,787. So now we've got to get something that starts 0.787. So some amount divided by 47 is equal to this. What should it be?
$37.
Okay, and what is it? How does it continue? 787?
It's 787-234-04-26.
26. Okay, and we'll throw away the 6. So we'll have 234,042. All right, so now we've got to start 0.042. So what will this be?
Let's try 2.
Okay.
So 2 divided by 47, it's 0.0425531915.
915, and then the 5 will throw away. So 0.0425, whoops. If I can get this back away. 553191. Okay, so now we need to find one that starts 0.191, some amount of 47s.
9.
Okay, and then how does it continue?
4893617.
Okay, we'll throw away the 7. So we're going to come down. I'm going to wrap it down here. 489361. All right, so we're going to come down with 0.361 now. So 947, or not 947s, some amount of 47s. What should it be?
17.
17, okay. And how does it continue?
36170.
Oops, sorry. 70.
21. Then 277.
And notice a couple things here. First of all, we're back to our beginning with 0, 2, 1, 2. Also notice that this 7 is, which we would have thrown away. It's really the 6 that's up there, and it basically got rounded. But that's all good. So all we have to do then is just put a 7, and we're done. And it should be 46 digits. So if I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. So in fact, we did need to go all the way back to 46 digits. 46, we had to do 46 different remainders before this long division process got back to the beginning. So this is where the bar is. The bar is on this whole thing, and then it would start back over with 0, 2, 1, 2, da 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 da. So that's what this one is. I've had a lot of fun with this with students in class where they collaborate with their calculators to find the digits, on the board and try to find the whole thing. That's usually all I do in the first day, but there's a part 2 for making the remainder web for 13ths and for 11ths. They have a different pattern to them that doesn't go through all of them. So that's kind of fun to see. And then number 3 is just doing the same thing we did the first day with 1/29ths, so that they get a chance to try that again and understand how it works. And then part 3 is really digging into going between decimals and fractions. So 0.257, knowing that that's 257 thousandths, so you can put 257 over 1,000, and just sort of reviewing that with the students, writing different decimals as a fraction. And then page 2 shows how we can actually turn repeating decimals back into fractions. There's an example up there at the top. I'm going to do one of these down here. So if we start with number 9, which is 0.4, repeating, the trick that's really fun to use here is to say, well, let's let x be equal to 0.444444 forever. And if we take 10 copies of that, 10 times that, multiplying by 10 moves every digit up 1 place value. And so we end up with 4.444, And when we subtract these, we get 9 x's on this side. And on this side, all of the decimal parts cancel out and we just get 4. If we divide both sides by 9, we get x is 4/9. And in fact, if you take your calculator and you do 4 divided by 9, you will get 4s forever. So that's showing how to do that. If we do the same thing for 0.79, for this one, 797979, etc. If I only multiplied it by 10, the problem is that the digits wouldn't line up and subtract each other right. See how the 9s are above the 7 and the 7s are above the 9. So we don't want to do it that way. What we really want to do is, instead of multiplying by 10, we're going to actually multiply by 100x. And what that does is it shifts all of the decimal places up by 2, all the numbers up 2 decimal places. And we get 79.797979. Subtract 100x minus 1x is 99 x's, and we get 79 on this side, and divide, and we get 79 99ths. And in fact, if you take 79 divided by 99, you will get 0.79797979. So these are some different challenge problems for the students to try to expand on that idea of how to turn any repeating decimal back into a fraction. And then the final part is really digging into rational versus irrational numbers. So is it possible for a rational number to have a decimal form that does not repeat or terminate? No, because any rational number either has to stop or it can only have so many remainders before it has to start repeating, which is what we saw in the first activity. And then suppose we have a number whose decimal representation repeats. Does that have to be rational or could it be irrational? Well, we just saw in the last example that we can always turn a repeating decimal back into a fraction using that technique. And so that's how we can find it. And number 3, here's an example of a number, 0.1234567891011121314. And it goes on like that. Is that rational or irrational? Well, this is an example of an irrational number because it doesn't, even though there's a pattern to it, it's not repeating in any, over and over again. And the same thing on the next one, though, it's 0.123456789123456789123456789. That is repeating, so that one's rational. On number 5, it's got 0.1001000100001, like this. But again, even though there's a pattern, it's not repeating, so it's irrational. Here we're looking for numbers between numbers. So can they write a rational number that's between 0.002 and 0.003? How about an irrational number between there? Can they think of one that would be irrational? Can they write a rational number that's between 0.12121212 repeating and 120120120 120 repeating forever? That one's a little bit of a trick question because the 120 is actually smaller. 0.120 is actually smaller than the 0.12 repeating. So they're actually reversed, but and then try to find a number that's between these numbers. So there's another example. And then the final one is just a fun proof that's playing with this idea a little bit. The first one shows that if you have 0.99999 repeating, that's equal to 1, and that uses the same technique we went over before. But the bottom one is a little bit of a surprise. So we have, this time, we're going to let x be equal to 9s forever to the left. So they're actually repeating this way. And there's the decimal point. And if we multiply by 0.1x, a tenth, then when multiplying by a tenth is the same thing as dividing by 10. So all the decimal places shift 1 to the right in this example. So you get this. And when you subtract on the right-hand side, well, all this stuff cancels out and you just are left with 0.9. And 0.1x minus 1x is negative 0.9x's. If we divide by the negative 0.9, we end up with negative 1. So what we've learned is that if you have 9s repeating forever to the left, that this is the same thing as negative 1, which should be weird. A surprise that something that seems really big comes out to be equal to negative 1. But it kind of shows the limitations of this method in a certain way. The thing about 9s forever to the left, and the reason that we don't normally write bars going to the left, is that this isn't really a number that's on the number line. This is basically infinity. It's getting bigger and bigger and bigger. And so it's not really legitimate to even write that number down in a way. And so that's part of the problem with this. If that number existed, it would somehow be equal to negative 1. There is a fun way to think about this as being a true result, though. If you thought about your odometer on your car, what number would it show right before it rolled back over to 0? Suppose you could drive a really long time. Right before it all flipped back over to a 0, it would show all 9s, which is kind of like this. So there is a sense in which this is true. If you had like an infinite odometer and it could roll around in that way, but it's not really a legitimate thing. So this bonus, that last one is just to make your students think a little bit and have fun with that idea that we've been playing with. Okay, so I hope that you guys have found that some of these games will be fun for your students, or activities will be fun for your students to do. And I am happy to stick around if anyone has any questions or things like that. Thank you so much for coming today. Thanks, Lance.
Thank you, Amanda. It was a pleasure. I'll keep things open a little bit while people are here. I think our program had a discussion scheduled, which I think we had time to discuss with the activities, but I think Pam has been here all day too. Thank you, Pam.
Yes, thanks, Pam.
Thank you. It was very, very interesting. Thank you.
Thanks, Lana.
Good stuff again, Dave, Amanda, Pam. Thank you.
All right, our pleasure.
David and Betty signing off here.
Thank you very much for your informative, everything was informative and directed to grade level. So thank you very much.
You're very welcome, Ms. Welsh.
Thanks. Thanks, Marge.
I just want to say thank you. This is Patricia Begay.
Hey, Patricia. Thank you.
I enjoyed it, especially when you brought up that the numbers can be read in Navajo. So that was very, very interesting, even though my phone kept cutting off. But
Yeah, that NIM game is a good game for practicing both Navajo and number sense at the same time. So you can say, I'm forgetting how to say adding now, but you can basically say like 0 plus 2 is 2, and then the other person can say 2 plus 3 is 5. So you can actually have them practicing their numbers in Navajo while they're trying to play the game. So it's a really good one.
Yeah,
That NIM game.
yes, I'd like to try that in my class. Thank you.